let me welcome everyone back to qmeets. We have been on our summer break. I don't know how carefully you read the last announcement mail. We have a very nice lineup for the next months and actually weeks. The next talk is in 2 or 3 weeks. We have a nice talk also in December and many different topics. Yeah, so stuff about quantum optics. Then we go to Rydberg systems, then some quantum thermodynamics, and also particle physics, the first direct detection of antineutrino scattering in the elastic regime. So there's a lot to be looking forward to, but let's focus on today. So today we have, and we're actually very grateful to have two extraordinary researchers and speakers, which are Časlav Brukner and Flaminia Giacomini. And as for every qmeets, let me try to gratefully introduce the two. So Časlav did his PhD with Anton Zeilinger in Vienna, I think before the new millennium. And after some time, he became a full professor in Vienna, where he still is until today. His research is mainly around quantum foundations. That's also the name of his group. And quantum information theory. He has made major contributions to entanglement, also from this information theoretic perspective. There is this paper on where your discord can be non-zero, so the quantum discord, and when not. He also published a lot on Bell tests, quantum gates, and after 2012-13, he started to look into things that are really interesting and novel, and this is stuff like indefinite causal order, together with Ognjan Oreshkov and Fabio Costa. And then when Flaminia became his PhD, quantum reference frames. And this is directly leading to Flaminia's CV. So she did her PhD with Časlav, I think now 6 years ago. The period ended. She is now an assistant professor in Rome since this month, if I'm not wrong. And in her PhD, she considered, together with Časlav, a very fundamental and deep question that the two will talk about today, namely, what happens if you attach this idea of reference frame to the quantum world? But she also thought a lot about things related to gravity. So, are there quantum generalizations of covariance and equivalence principles? How can you define causal structures in the definite and indefinite regime? What are quantum clocks? And of course, also the gravitational induced entanglement experiments, where she had a recent PRX. Congratulations. We are very happy that you're here, and now the stage is yours.
Well, thanks a lot for this really nice introduction. I mean, we don't deserve so much, so thanks a lot. And so it is our pleasure to be here to give this talk. And hopefully we will manage to convey the general idea of what is now actually, I would say, a small research field, still small, but growing and developing. So, that is quantum reference frames. And actually, this brings me to the first slide of the talk about quantum reference frames. That is just to set the history of a bit of this field, because there is a very funny coincidence. So quantum reference frames have been discussed since the 60s in quantum information and quantum gravity. And actually, the first paper in both communities is from the same year. In 1967, there was in quantum gravity this paper by Bryce DeWitt, where he advocated for the need of having material reference frames in quantum gravity. And in the same year, in this paper by Aharonov and Susskind, instead is basically the first one that introduced the need of having a quantum reference frame in a quantum information scenario. So in this case, it was related to conservation laws. And so basically, the two communities proceeded along their own paths since 1967, and they didn't really cross the different research lines. So basically, this means that basically now we have multiple ways in which we mean quantum reference frames. So when you read the word quantum reference frame, you should be careful to what you attribute it to. And we have, so basically from this paper here, the quantum information approach was developed. And from this paper here, all the literature in quantum gravity about quantum reference frames came. And then there are also efforts in quantum foundations. This is what we will mainly talk about today. And of course, now I'm dividing into these fields, but the distinction, especially now, is not sharp because the recent literature has more and more tried to connect these different frameworks. So now there are really papers at the interface between the two, and you would be able to attribute them to like 2 or more of these categories. Okay, so but one common goal of all the work that has been done is that the idea that reference frames should be associated to physical systems. And even though each framework tries to do that in a different way. Sorry, I have the Zoom in front of the slide, so I don't see what I'm presenting. Okay. I'll try to move it to a place where it doesn't bother me so much. Okay, let's do that. Okay, good. So this is all to say that we will present our own perspective on quantum reference frames, but we encourage you to go and look for everything else that is out there, and for time reasons, we don't have time to present. Okay, so what is the idea here? So let's start with what a reference frame usually is. A reference frame is usually a set of axes and a state of motion. And it is very useful because we fix the point of view from which we carry out observations by fixing a reference frame. So basically, this tells us if we have an experiment, who presses the button to detect a certain outcome, who prepares the quantum state, and so on. And a very general principle of physics is that all reference frames are equally good for describing the laws of physics. So in the end, it doesn't really matter which reference frame you choose, as long as you take everything into consideration. And in quantum mechanics, a possible change of reference frame, the easiest one is, for instance, translation and boosts. And they are represented in this way, where the translation, here we have the momentum, that is the generator of translation, and this x0 is the relation between the old and new reference frame. So basically, it's the amount by which I translate. And here, this v is the relative velocity between the 2 reference frames from which to which we are going. But what is important is that these quantities here, x0 and v, are not dynamical quantities and are not quantum. So they enter as a parameter in the transformation. And this will be crucial for us in the following. So in addition, we know that we have dynamics in quantum mechanics, which is governed by a Hamiltonian. And whenever we change the reference frame, then we say that the physical laws are covariant if they transform according to this law. And this is basically nothing more than what is required to transform the Schrödinger equation into a Schrödinger equation. Finally, we say that we have a symmetry of physics if the functional form of the Hamiltonian after the transformation is the same as the functional form of the Hamiltonian before the transformation. So for instance, free particle is mapped to free particle. Okay, so this sets the stage for what will come later. Now, what is the question that we want to address with quantum reference frames? So now imagine that we have three particles, A, B, and C, and we want to describe physics relative to one of them. So this follows a more operational perspective that says, well, whenever I make an observation, I use a physical system. And whenever I want to describe something, I take as reference another physical object. So for instance, we could choose to take as a reference one of these rocks. And then, for instance, C will describe the relative position of A and B with respect to the yellow rock. And A would instead describe the relative position of C and B with respect to the green rock. But now imagine that these rocks are actually quantum systems. So you don't have a well-defined state of one of these rocks, but you have something that is fuzzy, it's subject to quantum uncertainty. And now the question is, can we put a reference frame on top of this quantum rock? Does it make sense to ask how A sees B and C if they are in a quantum relation relative to each other? And this is the question that we try to ask in this framework. And what we will say is that, well, actually, if I stand in C, I can only say that I see A and B, but I do not know how I describe myself. It doesn't make sense. In a way, if you want, this is related to the self-reference problem. And if instead I take the perspective of A, I will describe B and C, but I do not describe myself. And this is the heart of the relational approach that is also something very common and quite transversal to different approaches to quantum reference frames. So the idea that physical information is encoded in relational variables. So for instance, relative positions, relative angles, relative velocities, and so on. Okay, so let us stick to the simplest case. We have three particles, A, B, and C. We start from C and we want to end up in A. And we want to just do a translation. So a transformation to relative coordinates. Then imagine that we set the origin of our reference frame in C. We have a system B, and we want to move the origin of the reference frame to this other point alpha. So in quantum mechanics, we just apply a translation operator that moves the origin of our reference frame here in alpha. And then we go to the relative position, xb minus alpha, basically. But now, if instead of having something sharply defined, we have a quantum state here that has some dispersion, then we cannot do this anymore. We do not know by which amount we should translate, which alpha we should put here, because, well, this state is spread. So what does it even mean to describe the system of B relative to A? So what one can do is to take seriously the linearity of quantum mechanics and say, okay, well, I just translate by every possible position in the real axis, but then I know that, for instance, this point is much more likely to happen than a point down here. So I should weigh the translation by the quantum state. And I want to do it in a coherent way because I want to preserve the linearity of quantum physics. And so this brings us, I cannot show you the calculation, but it's actually pretty simple, to an expression like that. So what have we done here? Here we had the parameter alpha, and instead here we have a quantum operator, xa, that is the position of a new physical system that we have introduced, that is A, that is the Hilbert space on which our quantum reference frame lives now. Then this is not the end of the story, because then if we go to A, then we should describe C. And so we introduce this object that is called the parity swap operator that basically realizes this part of the transformation. So the fact that A sees C in minus the position of A from the perspective of C. So you really just, if I see somebody at position X, this somebody sees me at position minus X. This is the idea of the parity swap. And then altogether, this actually realizes a unitary transformation that acts in this way on the quantum state. So rho AB is mapped to, from the perspective of C, is mapped to a state of rho of B and C from the perspective of A. So for instance, let us consider an example. We have a quantum system that is sent, so we have a quantum reference frame C to start with. So basically this flags the origin of the reference frame. And then we have a new quantum reference frame A that is in a superposition of two positions, x1 and x2. And now I want to move to the quantum reference frame of A, and I want to describe B and C. I apply this transformation here to this quantum state, and now you see that whenever this xa hits on x1 and x2, it will translate B by a different amount. So if I do that, then I find that B is in x0 minus x1 when C is in minus x1, so basically when A was in x1. And it's in x0 minus x2 when A is in x2 and C is minus x2. Okay, so this is basically a summary of what I told you already. That is that the fact that we have a transformation where we have an additional Hilbert space of the quantum reference frame, and the transformation acts as a quantum controlled transformation where the control is the quantum reference frame and the target is the system B in our case. So what do we find? So a first thing that you see it immediately here. So this was a product state. This is an entangled state. So one of the first effects of a quantum reference frame transformation is that superposition and entanglement depend on our choice of the quantum reference frame. They are not properties that are defined a priori. And this is quite natural if you look at the structure of this transformation, because this is exactly an entangling transformation. And then I presented you only the simplest transformation, but we have extended, like we can come up with as many transformations as you like if you want. And so far, everything that we have found is a superposition of classical transformation, so a quantum superposition of transformation that we can roughly write in this way, where this is a standard reference frame transformation that can be of different types. And this thing here is the control that is the state of the quantum reference frame. And of course, now, well, the question is, can this be generalized? Okay, and so now this is a very, very quick introduction to this framework, but then what can we do with that? And this is what the message that we really wanted to pass. So as I mentioned, these quantum reference frames can be useful for different fields. And in particular, I chose these topics just because these are the ones that have been studied within this framework. But there are many more if you look at other approaches to quantum reference frames. So in particular, we started from quantum foundations. So in particular, this first paper that I just talked about looks at how to extend the covariance of physical laws when we have a quantum reference frame. We talk about how we can talk about a quantum rest frame, so basically the rest frame of a particle that moves in a superposition of velocities. And this can be useful if you want to define internal quantities operationally, like internal energies or the spin, and in particular in special relativity. And we used this operational definition of relativistic spin also to come up with a relativistic Bell test. This is something that Časlav will tell you later. But it also has applications in a field that is closer to gravity and to quantum gravity. So for instance, extensions of the equivalence principle, definition of relational observables that is actually quite transversal among all these three. Symmetries are really the core of what quantum reference frames are. So it's a really important topic. And then studying the local tensor structure and so on. So these are just some topics, and I don't have time, but I'm happy to discuss them in the discussion part or in the questions. Okay, so now I just want to give you a very quick example about the generalization of the equivalence principle, and in particular the Einstein's equivalence principle. You can also do it for the weak equivalence principle. So imagine now that we have a system in a quantum superposition of different paths. So whenever you have, basically imagine, like, for instance, it's a system that acts as a clock. So if we have, as soon as you have a reference frame well, a system in this case, or a clock that is delocalized, quantum delocalized across a portion of space-time, then the usual assumptions that we need to define the equivalence principle do not hold anymore. We are outside of the usual scope of the equivalence principle. This can happen also on the surface of the Earth, where gravity is the same, but the objects with which we test the principle are quantum. So basically, this calls for an extension of what the equivalence principle is that can be done to quantum systems. And the natural extension is using quantum reference frames, because, well, the definition itself of the equivalence principle relies on like local inertial frames, basically. But if you have a clock that is in a quantum superposition, then you have local inertial frames that are in a quantum superposition. And this is exactly what quantum reference frames can do. So what we did is to, in this set of papers, we have generalized the Einstein equivalence principle to two different situations. One is this simpler one, if you want, where we have still a classical gravitational field, but the particles with which we test it are quantum and delocalized. And actually, if you consider this situation, you can come up with a test of this extended equivalence principle in atom interferometry using quantum clocks. And a result that I don't have time to show you is that if basically, if the extension of this equivalence principle is violated, then this invalidates the concept of what the frame of a quantum reference frame is. So it basically, it is, well, I would not say impossible, but it becomes much harder to be able to define what the quantum reference frame of this clock is. And then there is something that is a little bit more speculative that we looked at with Časlav. And when the gravitational field itself is in a quantum superposition, and then you have that a particle can become entangled with the gravitational field. And in this case, you're really out of the standard definition of the equivalence principle, and you can define an extension of the equivalence principle that is valid for a gravitational field that is in a quantum superposition. And this also relates to Perrow's spontaneous state reduction. Basically, if this generalization of this Einstein equivalence principle holds, then we can overcome one of Perrow's criticism that led him to the formalization of the spontaneous state reduction. Before I hand it to Časlav, let me just comment that I mentioned that this is a superposition of gravitational fields. But what does it mean? So in general, we don't know what it means, okay? Because we don't have a full quantum theory of gravity. And so we cannot rigorously formulate in all possible cases what a quantum superposition of space-time or of gravitational fields actually is. But there are some cases in which we can. And this is the case when we have a massive particle in a quantum superposition of sharply localized positions. So basically, in this case, effectively, if the mass is on the left, we have a classical gravitational field corresponding to this state. And if the mass is on the right, we have a classical gravitational field for all practical purposes, in the sense that experimentally we don't measure any deviation, that the mass is on the right. And then we linearly superpose that, and almost by definition, we get a superposition of classical spacetimes. But then, using quantum information thinking, we can extrapolate that to some general principles. And these are that we can have macroscopically distinguishable gravitational fields that are assigned orthogonal quantum states, that each well-defined gravitational field in the quantum superposition is described by general relativity, and that the quantum superposition principle holds for such gravitational fields. So we do not know exactly up to which regime we can extrapolate this notion of classical gravitational fields, but as long as these three assumptions hold, then we can talk about that. Okay, so that's all I wanted to tell you. And so the take-home message from the part of my talk is that quantum reference frames can connect different areas of physics. I talked about quantum information, quantum foundations, and gravity, quantum gravity. And they are useful to solve open questions. And I gave you, as an example, the Einstein equivalence principle. And now I will just hand it to Časlav to give you additional examples. Thank you.
Thanks a lot, Flaminia. So now it's time to ask the first round of questions, regardless of whether it's on understanding or further topics. However you like, just feel free, unmute yourself or raise the hand in Zoom and ask whatever comes to your mind. To get things started, I actually have a question related to your last slide. You said that... Oops. No, don't worry. You said that in certain regimes, the construction you just explained can hold. Are you referring to you just work in linearized quantum gravity, or do you also have indications that it works beyond, or?
So what we can do, okay, so the only place where we can actually rigorously formulate what this what superposition of classical spacetimes is linearized quantum gravity. Yes. Apart from that, we do not really know what that is. And so this is why we resort to this quantum information concept. We postulate some assumptions and we stick to those assumptions.
Okay. So yeah, I guess it's related to the field equations are also linear, so everything is simply linear in the end and fits together.
Yes.
Okay.
And especially we have a framework. We have a framework that we can use to calculate what that means.
Yes, yeah, true. Okay, thank you. Further questions, guys?
Actually, I have a question.
Yeah.
So regarding the first part, at some point you present this operator to switch between B and C, right?
Yes, the parity swap, yes.
Exactly. I was just wondering, can you also develop something like that when you want to switch towards an accelerated frame?
Yes. Yes.
Okay.
Yes, we have it. So in particular, in this same paper that I'm this one here, we also have the transformation to an accelerated frame, uniform acceleration. And then you have to modify the parity. I mean, you can see it in two ways. Either you modify the parity swap, we call it generalized parity swap in the paper. And this basically because what you want at that point is to really invert the equations of motion. And compared to what we have here, we need to add some ma divided by mc somewhere on the momentum in particular to really switch the equations of motion. And so you need to add the operator that does that. And I mean, you can add it inside the parity swap and then modify the definition of the parity swap, or you just add it as another operator in the transformation. So this doesn't really matter as long as it's in the transformation somewhere. And but that is basically it. And you could do it also we tried also to do that for non-uniform accelerations. This is a little bit more complicated because, well, calculations are harder. And so in the end, what we did was some sort of trotterization to do like at every small delta t, and then we sum over the intervals. But yeah, so this is a little bit more complicated for general accelerations. One could do that.
Thank you.
I think Victoria was slightly faster, so please go ahead.
Okay. Hi, Flaminia. Super nice talk. I have a small question about the testing of quantum gravity. I just saw a talk last week that instead of putting the masses in a gravitational superposition of that, they were doing it via the angular momentum as well, the entanglement. So are you aware of this? Do you know other kind of tests of the non-classicality of gravity?
Yes, yeah. So now I think so one direction in which the community is focusing is to find alternative tests that are either easier to realize than entanglement-based tests, or like would tell you more basically about the quantumness of gravity. And I think the one about the angular momentum, so at least from what I remember, because I looked at it some time ago, I don't know if Časlav has it fresher, but from what I remember, that one there, it's nice because you don't really need the different states of motion, but you can just superpose angular momentum, and that is a little bit easier. And I think it would also involve something that is more relativistic than the simply the entanglement imposition, if I remember correctly.
May I just kindly ask, could you maybe for the audience provide some reference or what they need to look up when they want to learn more? Like just angular momentum and...
Can I send it in the chat later? Because now
Yes,
I cannot
please.
type. Yeah, I will send it in the
This
chat
would be
later.
very nice. Okay, it's nice. Thanks. And then we have Abhijit. Please go ahead.
Hello, could you hear me?
Yeah.
Ma'am, it was a nice talk. I just wanted to ask if there would be some merit in looking unitary evolution as a reference frame generated by the Hamiltonian.
Okay, sorry, I missed this.
Ma'am, you had shown some examples of reference frame changes, right? Generated by translation or Galilean boost.
Yeah.
Could we look at unitary evolution as a reference frame change? Because
To
it
a
has the
unitary-
same structure.
You mean for the Hamilton unitary evolution in time?
Yes, ma'am.
So what I can tell you is that, so once you get this transformation here, then you can get the Galilean boost. And then, so basically the Galilean boost roughly it's PAXB plus other stuff. But the important part is PAXB. So you immediately see that this does not commute like the usual Galilean boost and translation in quantum mechanics, because you have also these operators here that create troubles. And then you ask, is this a group? And it's not immediately obvious that this forms a group, but it does. It forms a group. It forms a Lie group it has 7 generators. And among the generators of inertial quantum reference frame transformations, you also have the Hamiltonians, the free Hamiltonians of the particles, A and B in this case. So in this sense, yes, the Hamiltonian itself is a generator of the group of quantum reference frames, of inertial Galilean quantum reference frame transformations.
Okay, so you're saying it will depend upon the exact nature of the transformation.
Yeah. Well,
Thank
inertial, it has to be inertial.
Thank you.
Then we have Clement.
Yes, hello. So I wanted just to know a bit more about why your results overcome the Penrose collapse of the wave function, if it's possible.
Okay, yes. Okay, so maybe it's easier if we look at an example. So imagine now that we have a big mass like the Earth and an atom in a quantum superposition. Now we jump on the quantum reference frame of the atom, and we see that the Earth is in a quantum superposition. So if the quantum reference frame reasoning is true, then these two situations are equivalent. So we should have cases in which the Earth is allowed to be in a quantum superposition and the atom is localized, and this should be equivalent to when the Earth is localized and the atom is in a quantum superposition. What Penrose instead did is that so for small masses, it's fine, they can be in a quantum superposition, but as the mass increases, basically you have this spontaneous state reduction. That means that one of the amplitudes dies out and you go back to a classical metric. So there is an instability. One of the two disappears over time, over this delta t that he defines. And then you go back to classical metric field. And he has several ways of arguing that, and one of them is because the principle of equivalence is not reconcilable with the principle of linear superposition. This is this argument. But you see that now that there is a problem if you adopt the quantum reference frame perspective, because for us, if we come from quantum reference frames, then we shouldn't have any reason to prefer the small mass to the big mass. Both of them should be in a quantum superposition. And so this means that if you introduce I don't want to say collapse, but this reduction model, then you are violating one of the essential conditions for quantum reference frames to be valid descriptions, to be valid perspectives from which to describe physics. And so but if you say, well, we cannot save the equivalence principle if a mass is in a quantum superposition, then we also have a problem with quantum reference frames, because the equivalence principle is sort of important. We like it. And then the way around that is that, okay, true, the equivalence principle doesn't hold in its usual form, but we can extend it. And if we take this extended equivalence principle, then we can save everything.
Okay, that's a bit more clear. Yeah. Okay. Thank you.
Okay. So let's thank Flaminia again. You will have the chance to ask more questions later, but now it's time to hand over to Časlav.
Okay, thank you very much. Before I start, I may prefer, because otherwise we will forget that, there was a question by Tobias Yu, which somehow I think hidden behind that could be something which might confuse or be misunderstood. And it's about the nature of this superposition of spacetimes. Flaminia said that we know how to handle this in linearized quantum gravity. And then I think Tobias said, oh, of course, because everything is linear. Something along these lines. And I want to make a remark that one should distinguish nonlinearity of Einstein's equations with linearity of the quantum reference frame approach. They are not in contradiction, because what we linearly superpose are solutions of the Einstein's equations. So that these solutions can be obtained by the nonlinear dynamical equations, that's something different. So no matter, even beyond linear quantum gravity, what I was saying, it's not there is no obstacle immediate to extend the idea of linearly superposing solutions, or maybe something more general than Einstein's equations within the approach of quantum reference frames. So that's all. So yeah, thank you very much for the invitation. So let me then start my talk. It will be quite personal. For 20 minutes, it's hard to be objective, and it's hard to give really a full perspective on the potential of this quantum reference frame approach. So I made a selection. The selection is very private, and I also make a selection to the most simple examples. But we can, of course, talk then later on about more complicated situations. I named this as invariance and the quantum reference frame transformation. So I'll try to give a perspective only on one, but very important, maybe essential aspect of quantum reference frames transformations. So here is the picture that we often use as an opening slide. We somehow divide the systems around us in two categories. And we say, well, one of them serves as a subject of investigation, and the others are rather reference frames. So we have clocks and rods as a reference frame to describe other systems. But maybe what is the basic idea of quantum reference frames is that there is no essential difference between these systems. It's just convenient to take some of them to describe others, because after all description is relational description, so certain system relative to another systems. And because the quantum theory is the most fundamental theory, we should also describe reference frame from this perspective and treating all of them as quantum mechanical systems. So here's the context of this short presentation. I will introduce the notion of an invariant observable. Then I will make a distinction between invariance under classical and quantum reference frame transformations. Then I will give a simple example where we can apply that along the lines what Flaminia already said. A quantum gravity scenario, a typical, the most simple one. And then I will move to another kind of invariance under quantum reference frame transformation. And this is a combination of entanglement and coherence. And finally, I'll conclude. So when we talk about invariance, I'll start always from idea that for certain observables or measurements, we might not have an external reference frame. For example, if this observable is a position of a particle, if there is a lack of external reference frame to determine this position, then only relational observers are physically meaningful. So you can think about the position. If we don't have any external reference frame, only the relative distances are physically meaningful. And these are then invariants under symmetry transformation of some group, in that case, translational group. If you want a little bit more formal, we will say that observable is G invariant if this relation through the unitary representation of the group element on this observable leaves the observable invariant. And that's true for example, relative distance in the case of translational group. Now here is example. We have two balls, and we believe that only what is relevant is the relational distance between these two balls, because this is what figures into the potential or interaction of these two balls, maybe gravitational interaction, and the free particle, kinematic particle, or part of the Hamiltonian. Now, exactly because of this irrelevance, where we choose the reference, origin of the reference frame, we may, and now colloquially speaking, jump on the first ball or choose the first ball as the reference frame through this transformation, which will leave the Hamiltonian invariant, and we will say then that we have a symmetry of the system, or that even the dynamical laws that are based on this Hamiltonian will have the same form, no matter whether we choose the first or the second coordinate system. And now, what Flaminia already introduced step by step, the next step from taking these two systems to be classical, you can think about one of them to be quantum mechanical, let's say B system, and C and A to be a classical reference frame. Maybe the walls of the laboratory is one of them, and the other one is the optical table. So this is the situation which we are well known in quantum mechanics. We know how to move from one to another reference frame. For example, in case of translation, we will have these generators, shift operator, where the generator of translation is the momentum of the particle we want to translate, and XA is some classical parameter. And finally, what Flaminia already introduced, is the situation in which we think that all possible relevant reference frames are as quantum as the system under investigation. So we can think about having a C point of view where we do not refer to ourselves. We avoid any self-referential statements, but with C, A, and B in some general quantum mechanical state, and then may move from C to A through this transformation, which, as Flaminia said, is quantum controlled translation. You translate B for the parameter that depends where A is, and finally you just parity swap between A and C, and you can have different situation. On the right hand side, this is something which is close to the classical reference frame transformation if we think about A and C being well localized, whereas the left hand side is something truly quantum mechanically, where, for example, the new reference frame is in a clear superposition of two localized states, such that when we jump on A, the rest becomes even quantum mechanically correlated, although it wasn't in the first frame. Now, if we talk about invariance and the quantum reference frame transformation, we may start with the very same problem, that there is a lack of external reference frame for the measurement of an observable, such that still relational observables are physically meaningful. But because now we consider reference frame to be truly quantum mechanical, we are then bounded to a more general set of transformations, which are invariant, and observables, which are invariant on the quantum controlled symmetry transformation of the group G. We have seen this already in the case of translations, but we can think about any group, as it was done in this paper 2020, for any group in this paper was done that what is the quantum reference frame transformation is quantum control unitary representation of the group of transformation, and then this parity swap between two reference frames. So we may ask ourselves, under this transformation, what are the observables that keep their functional form? Let's say we express this in some Hilbert-Schmidt basis, these operators, and we require that the functional dependence of the basis of this Hilbert-Schmidt operators or basis operators is the same from C point of view on A and B as from A point of view on BC. So we do exchange the systems, but we require the functional form to be the same. And if we go back to the translations, then an example of these operators that are invariant under quantum control now translations is, for example, relative distance. So the relative distance between B and A, as seen from C, will be equal. You can think about absolute distance from the A to B, but this is just because we are sitting on A, and we, by definition, say that the A is in the origin. But this is the same functional form as before. And similarly, for example, for the momentum of the B, if you apply this transformation. So we see that some of the observables keep their invariant form under these quantum reference frame transformations. And this brings us to perhaps a way to deal with some situations which we are not used to in standard approach. Here I have two physical situations. Now, unfortunately, when you combine the slides from different talks, the notation is not always preserved. So I had A, B, C before, but now I have R, S, and M. So R will be the reference frame from where I start from. That was the C in the previous slides. And then I have the new reference frame that will be this large M mass. And then I have a system, which was B in the previous slide. So imagine that you start with a situation, the left-hand side, and you might be very ignorant or neutral with respect to how you should solve this problem, because obviously the mass in a superposition and therefore also gravitational field is in a superposition, and you might be then having a neutral position of how you can treat this situation because you don't put any preference on any of the approaches to quantum gravity. But then there is another situation, and Flaminia mentioned this in the answering session, where you can move from this reference frame to another reference frame by jumping, so to say, on the mass and making the mass origin of your new reference frame, in which the other parties there, S and R, become quantum mechanically entangled in the general sense. Now, when you look at the Hamiltonian, which is here time-independent Hamiltonian, the Hamiltonian, in which you assume that R is very far away and not gravitating, and mass is also very massive and not dynamically have a kinematical form of dynamics, then you have a kinetic part of the system and gravitational interaction. And this Hamiltonian preserves its form when you move to another frame. So this is an example of Hamiltonian as a symmetry of this problem, as invariant under quantum control translations. And that should suggest that maybe you can also extend the invariance or symmetry of this problem, assuming symmetries that are under the larger set of group of transformations, namely invariance under quantum controlled translations, or more general quantum reference frames or quantum coordinate transformations. Now, this can help you. For example, you might say, again, from this ignorant point of view or neutral point of view, that you want to solve the problem of the motion of a test particle S in a gravitational source in superposition. And you might say, I don't know, I don't want to put any interpretation on this, but I do believe that my Hamiltonian should not change under not only classical translations, and we are now in the Newtonian limit, but also under quantum control translations. So you may assume that there's nothing happen if I change the reference frame and sit on the M and then solve the problem. Now, this problem is known how to solve this. There are many approaches to that with different level of approximation. Once you solve this problem, you will see that the system S that is here in superposition of two locations will dynamically evolve such that you will have movement of the system in superpositions of two freely falling trajectories with corresponding phase. I didn't draw here R because it's irrelevant for this transformation, but you can solve in any case this problem, and you can go back in your initial reference frame and get the answer through this kind of commutation diagram from 1 to 4 directly then. And this is something that we try to argue for in the paper 2023. You might go also beyond Newtonian structural particle and think about the clocks and ask yourself how the quantum clock will tick in this superpositional space times and can also take this neutral position, but under assumptions of the validity of the extended symmetry principle, you might go into the appropriate reference frame, and then you know how to solve this. The clock in a superposition of gravitational, the clock in a superposition of spatial positions in a definite space-time is something which can be solved, and you will get certain difference in time dilation depending on where the clock is. The closer the clock is to the mass, the slower the ticking is as compared to the position further away from the large mass. And once you solve this, you can go back and provide the answer, what will happen in the original reference frame. Now, something very interesting was discussed at the question session. This is the difference between the Penrose model and maybe something which will preserve linearity in quantum gravity without taking any particular position here or any particular theory. And this is something which can be considered from the point of view of general covariance. So we have here 3 different theories that in 3 different ways treat the simplest quantum gravity scenario when you have a mass in a superposition. And imagine now, for concreteness, that not only the big mass is put in a superposition, but also that you have a small probe particle exactly in the middle of these 2 amplitudes. Now, the upper and lower row are the same situation as seen from different reference frames. And what I first on the right-hand side want to consider is so-called semi-classical gravity. And semi-classical gravity is the gravity where the source of by the gravitational field is governed by the average value of the gravitational field, average value over the 2 amplitudes. So what you have here, for example, in the lower part, is that we take the reference frame of the big mass. Now, the average value of the gravitational field is what it is from the point of view of the Earth, which is localized. And so if I have then in that reference frame a small mass in a superposition, what I will see that these 2 amplitudes will fall towards the center towards the big mass. However, if I look in the upper picture and still treat it as a semi-classical gravity, then I see that exactly in the middle of these 2 amplitudes, the gravitational field is 0. So nothing will move. So we see that depending on which reference frame we choose, the semi-classical gravity will give different predictions. Therefore, semi-classical gravity does not obey this extended symmetry principle. It might still be true, but that will mean that there are some, let's say, some quantum reference frames are better than the others. What is in the middle is the same for the collapse model, either Penrose type of collapse model or maybe collapse model of Girardi-Rimini-Weber. So again, we start with the lower picture in which the mass is localized and small mass is in a superposition. And that's exactly the example Flaminia was explaining in the questioning time. In this situation, because the mass is small, there is no collapse. So what we will see is that these 2 amplitudes will coherently fall towards the central mass. However, from the point of view of jumping on a small particle, the large mass will be in a superposition, but then the collapse model says, well, this cannot survive. It has randomly to go either in the upper part when everything collapses on the right-hand side, or in the lower row where everything collapses on the left-hand side with some maybe 50-50 probability. And again, we see that the physics in the 2 pictures, lower and upper, are different, and therefore collapse models are also not in agreement with extended symmetry principle. So the only thing that will still be in alignment of extended symmetry principle is that actually there is no any change in the physics when we choose one or the other reference frame. So either in the lower one, we have these 2 amplitudes going coherently falling towards central mass, or in the other picture, 2 masses also, if you want, falling towards the central small mass in superpositions. Okay, now I want to go a little bit into quantum information now avenue and discuss to what extent we can maybe expect some interesting phenomena when we extend the invariance to quantum reference frames. So sometimes people react that, well, it's nothing interesting there, because if we have something which is invariant under classical reference frame, then it's also invariant under quantum reference frame transformation branch by branch. This is very much in the many world interpretation point of view, or thinking like, okay, I can define any quantum superposition into branches of classical, and then I know that something is invariant in the classical, so it must be in the quantum reference frame transformation also invariant. And I wanted to ask, is this always the case? And in order to answer this, we look at something which is not a self-adjoint operator for a single copy of the system. One can still define this on many copies. I'm not doing that. But you can think about this as a more general observable that can be obtained through statistics measured on many copies. And what I here will consider is coherence. Coherence as one of the measure of how strong are off-diagonal elements of some density matrix. And I talk about coherence as something which depends on the basis chosen. So I take the basis of the group elements, and I look as the coherence to be a measure which is the difference in the von Neumann entropy of diagonal matrix in this basis. So you can think about maybe position of the B minus von Neumann entropy of the full density matrix. And another kind of collective or statistical observable is entanglement, and I will here take only pure states of the composite systems A and B, and entanglement B will be then just von Neumann entropy of the reduced state. Now, each of these quantities, coherence alone and entanglement alone, are invariant under classical reference frame transformations. Yeah, you cannot increase or decrease entanglement by just moving around or just maybe shifting your origin of the position measurement. So what is, however, interesting, and you have already seen that, is these quantities are not invariant under quantum reference frame transformations. And we already had this situation where we start, for example, with the product states, and where A is in a superposition of localized states, and B is factorized out. But when I jump on A, B and C become entangled. Of course, the opposite is also true. So we suddenly, by coming from quantum reference frame, classical reference frame to quantum, we have a new quality that something what was invariant under transformation of classical reference frame become non-invariant under quantum reference frame transformation. And then the question is, can one find a new quantity that nevertheless will be invariant under this quantum reference frame transformation? And that's something which we published this year, where we found out that the mere sum of the two, the coherence and entanglement, is invariant under quantum reference frame transformation when they are defined in the way through the von Neumann entropy as I introduced there. So indeed, although each of them can change, here, for example, we might have very large coherence, but no entanglement. When we move, we will have a large entanglement, but almost no coherence, in such a way that we have a kind of a conservation law, if you want, that the sum of coherence and entanglement is preserved by changing from A to C reference frame. And this is already my conclusion. I don't know how I'm doing with time. I want to say that I wanted to present a couple of simple examples of observables that are invariant and the quantum reference frame transformation. One example was Hamiltonians that can also then help us solve some problem, move into reference frames where the problem seems easier. And then there is really, to me, interesting phenomenon that coherence plus entanglement are preserved under this quantum reference frame transformation. I would be glad to see other, preferably single copy observables that have these features of invariance under quantum reference frame transformations. This provided possibility to explain dynamics of falling pro-particle and time dilation presence of gravitational source in superposition. That's something maybe for discussion. we are restricted to superposition of semi-classical states, as we discussed before. But these semi-classical states can be widely separated, widely different, such that none of them can be seen as a perturbation of the another or of some third state. So they can be really widely different from each other. And with this, I would like to thank you for your attention.
Thanks a lot. Okay. So now it's time for questions on Časlav's talk. I think at some point there was a question in the chat, and I think it was related to your slide where you have the two Earths basically and the different scenarios of whether you have collapse or not.
Mm-hmm. I can go through that again.
The person in the chat is saying that possibly he is not able to speak up because he's in a train. I will simply read it out loud.
Yes, please. Yeah.
Wouldn't in the top right the two Earths fall towards each other, giving a completely equivalent description?
Yeah. In a semi-classical, am I right? In a semi-classical thing? Okay, so imagine that you, it's interesting that this question is repeated, so definitely one could introduce this differently. So imagine that the Earth is in a big trap. Okay, so you trap the Earth such that it cannot move. So it's deep in a trap that cannot move. Then still, if you have a small particle left and right, they will be attracted and fall down. But in upper pi, it's not the case. So I can, and this is sufficient, I can have one situation in which I can make distinction between the upper row and the lower row. And that's one in which you, this mass is, for example, trapped, so I cannot move. That's all. So all what I want to keep then, these two things, to be such that in the middle of them, I have a zero field. So this small mass will not move, and the big mass will be also not moving because, I mean, this one big mass, sorry, not big masses, it's one big mass which will be trapped, and therefore it cannot be moved. And therefore I will have a phenomenological difference between the two positions, two rows. I hope this answers. I don't know whether person is online now.
Possibly Claudio will answer in the chat. But in the meantime, we have already another question. Yes, please, Victoria, go ahead.
Hi, Časlav. Very, very nice talk. I keep thinking about the part of the time dilation of you're using kind of your quantum particle with the time that in quantum mechanics, our time is a parameter, but with space-time, and space-time is a dynamical variable, I cannot get hand of
Okay.
how would that.
Good. So, I mean, my personal opinion about time is what clock shows. But so in the case I mean, in the case that I consider is indeed a clock, so we put a clock there. So let me go maybe back to this also for everybody to be seen. So I think this was yeah. So what you see here is indeed an experiment in which you have a clock, and maybe in the first picture the clock is localized. In the second picture is something which I hope people will soon also be able to observe. I don't know, I mean, people now observe the time dilation in the Earth gravitational field with two clocks, which are separated by less than a centimeters. I don't know what is the world record now. So, but here is a single clock, of course. So single clock put in the superposition of two positions, and there is, I mean, very little doubt, although this has not been done yet with a single clock, that if I would find this clock in one position, I will have one time, and if I found the clock in another position, I would have another time. And furthermore, there is little doubt that everything is quantum coherent, and that you can make some interference experiment, and I go back to some of the works that have been done with Magdalena Zich and so on. What you are asked, of course, in that sense, this is a time dilation of that clock in the gravitational field. Of course, we describe this situation very often in terms of the coordinate time. So this is not a proper time of this clock in the gravitational field. These things are usually described in a coordinate time. But I will preserve my position that time is what the clock shows, because even that coordinate time is a clock of somebody very far away who can describe this and does not get entangled with the mass and can describe this with a unique time. So in that sense, it maybe combines both intuitions about that. Yeah, time that is in this experiment is the local time of the clock, but you can also preserve your absolute time, which nevertheless can be seen as an operational time from somebody who is very far away. I hope this answers.
Thanks.
We have a follow-up by Claudio in the chat. I will read it again. I don't get how the large state would be trapped. That would require additional systems around. Or it is assuming that the Earth state does not feel its own gravitational field.
I'm not clear what it means. It is assumed that Earth state does not feel its own gravitational field, but I don't know why there would be physics breakdown if you take a large object to trap and a small object not to trap. Surely this trap will, let me see, this trap will certainly also, if you want, there is some potential energy, so will also require that this potential gravitates, but it doesn't matter. It's symmetrically. In the first picture in which the Earth is in a superposition, then also the trap will be superposition. You can add this gravity of the trap as well if you think that this trap gravitates because of potential, but it's all still symmetric. So in the middle between them, there is no gravitational field, and in the other case, there will be a small particle falling towards the big mass in the trap. I mean, I think of all these possibilities, semi-classical gravity seems the less plausible. I hope soon we will have an experiment when you just do that, what I said. So you put a large mass in a superposition, you shoot the particle in the middle, and the particle doesn't go through. It will start to be attracted either left if the mass is left, or right if the mass is right. That, if this happens, what I just described, this will be another, it will be explicit example of extending symmetry principle in work. If it goes through, it won't.
Okay, thanks for clarifying. I think there was a raised hand by Gaetano Fiore, but
yeah,
so please go ahead.
No, I have found the answer by myself. I had a question and I found the answer by myself. So it's okay. I have no more questions. It was something related to this semi-classical treatment of the two sources of, of the particle and the source of gravitational field. But if you want, I tell you what was my question and then what is my answer. But I guess it doesn't change what Časlav said. So that the essential thing. So maybe it's better I avoid. So I can.
Okay.
Yeah.
However you prefer.
No,
There
it
are
was
also
just,
other questions.
I mean, on the scales of a realistic experiment, what happens is what I agree with Časlav. My point was the following: in the perspective where you have you see the experiment from the point of view of the reference frame of the small particle, you have the big mass in superposition or in two different positions, opposite ones. So the evolution of the wave function in the long term would be to split one half towards one source and the other towards the other source. And so in the long term, the probability that it falls on the mass coming in one direction or in the opposite direction are half and half, and it's not staying still. But this happens on a very long time scale. And since in the region where the particle initially is, the gravitational field is practically zero. So in the short term, the particle remains still, essentially. The wave packet remains concentrated in the center. Maybe there is some spreading, but not very much, and does not separate into two parts. And so this is in this approach where the particle is still and you have two sources. Whereas in the other approach, it's the movement of the particle towards the source in one direction, the opposite is much faster. So there is definitely a different answer whether you treat semi-classically the sources with the perspective of one reference frame or the other. There is a difference. So I agree with you.
I think I understood. You are saying that if the probe particle, if we wait for long at this position in the middle, it starts to spread.
Yes.
And then through the spread, then even the semi-classical gravity would say that there could be some differences. Yeah. So you indeed, but it will be different than in the first
much
case.
Slower.
Much slower, and I can imagine that you shoot the particle very fast, such that it is very before the characteristic spreading occurs, and see whether it will be then deviated towards one or the other mass. But yeah, you are right that a more careful analysis has to be done. Yeah.
Yes.
So next up would be Nick.
Hey both, and thanks for these very nice presentations. And I hadn't thought of, there were a number of things I hadn't thought about before, but the discussion of coherence, I think was interesting. But the thought that occurs to me looking at the basic pictures. So in the C frame, B is not entangled with anything. In the A frame, it is entangled. So if I think about the reduced density matrix for the reduced state for B, in one it's mixed, in one it's pure, and that just seems like then there's going to be observables on B that are going to come out different. And where's the symmetry there? I'm sure you've thought of this, but what's going on with that? It's a
great question. This is it has its name. It's also a paradox of the third particle. It's related to that, what you're saying. But look, imagine, quantum reference frame transformations are unitary transformations. Unitary transformation means, in a sense, very trivial, because not only that you change the state, but you also change the observables. So you change everything, such that probability for any observation are actually the same. Now, they are interesting because they are not any possible unitaries. They are related to the symmetry transformation, extension of symmetry transformation, but they are unitaries, and therefore probability distribution cannot change by this. So if you think in one reference frames, there is a decoherence, then, and this decoherence you can measure by measuring, for example, the coherence of one particle, and you see that it's lost coherence. When you go to another reference frame, that might look completely different, but nevertheless, the amount of the coherence given the observables that you can access in this, not access, but that you transform from one reference to another will give the same result. So there cannot be any different predictions, no matter from which reference frame you look at some process with measurements and so on, as compared to another one. There is somehow, nevertheless, something very deep here, I think, and I think Nick is also pointing this, which I believe still needs an explanation. And that is, okay, if all quantum reference frames are equally well, there is no preferred quantum reference frame, how come that we live in a world in which there are these classical reference frames, and we all agree on them, like most of the things around us are classical. Okay, and I've been thinking about it, but I don't have any concrete results. And I think this question is very much related to the questions, well, if quantum theory has this unitary equivalence, how come that we end up in the coherent world in which there is classical physics for most of the systems? And some kind of decoherence is needed there. And now the question is, of course, how much you want to put into this decoherence. Can you think that, well, do you want to put additional elements like only local interactions? But what are local if all factorizations in Hilbert space are equally well? So the question is how much you want to put there. But nevertheless, I think whatever you try, you need to explain why we end up with this reference frame for which exactly this happens, that it's very unnatural to think about another reference frame having entangled state and so on and so on. And yeah, I hope we will be able to answer this question. I think we keep thinking about that. I don't know whether this answers your question.
Yeah, no, thank you. I think I see how the first part does, and that's very interesting. But I do this experiment. I do my sort of two-slit my interference experiment on the second system, but I'm measuring a different observable according.
Yes, you measure the
according to the two frames. Yeah.
Yes,
okay,
yes.
that's I get it. And the second part, yeah, nice.
I suppose that Flaminia also wants to say something here, or do you want to question Časlav?
No, I just wanted to add something to what Časlav said, if I may. Okay, so yeah, hi Nick. So I basically just wanted to add that. So I think there are different layers on which you can answer your question, and the thing that Časlav said is of course true, and this is because if you stick to the perspective of one quantum reference frame, you have a set of observables that you know are accessible to you, and then you measure them. And then you change the quantum reference frame, and everything is unitary, so everything is conserved by default almost trivially, because everything is unitary and the trace is cyclic under unitary transformations, basically. But there is another question that you may ask, and I think this is also related to your question. Imagine that I have a quantum reference frame and I have a set of observables that are given. And then I have another quantum reference frame, and for some reason I have a different set of observables that are given. So for instance, say I can measure positions in every quantum reference frame. for whatever reason. So at this point, under the quantum reference frame transformation, these are not mapped directly to the other set of observables. And if you have that, for instance, you have a system that is accessible to you, and then there are other systems that are not accessible to you, then the two descriptions will not match. So this is not a problem per se, because in the end, this just means that I'm doing different experiments in different quantum reference frames. But you have, well, two things. One is the paradox of the third particle that Časlav already mentioned. And the other thing is Wigner's friend, as soon as you make measurements. That immediately becomes a problem in the moment when you can make measurements, record an outcome, and you do not communicate the outcome to another quantum reference frame. And this is phrased in a much more general discussion on what is the coherence in quantum reference frames. And surprisingly, there is very little around that addresses that. And also the measurement problem in quantum reference frames. And I mean, if you have noticed, both Časlav and I, we have been careful never to mention observers, but always frames, precisely because of this reason.
Okay, we have another question by Noah. Please speak up.
Hi, I think my question goes into a similar direction. So if we look at our Earth and our atom or our test particle in superposition, so once we have our Earth in superposition, once we have our atom or our system in superposition, but what would happen if we go to a third reference frame where both are in a superposition? So for example, they could be in a superposition where they are in the same position.
I didn't get fully, but you can. Okay, so the step, I think, what is necessary and which we didn't talk about, but we both work on that, is the quantum. Of course, reference frames are not the same as a coordinate systems, because the reference frame has this kind of global thing. You know, I have a global translation, and then I can, of course, make one system being localized and the other not. But there is nothing which prevents you to go into the coordinate fields as a representation or generalization of the idea of quantum reference frames, where you can when you can localize independently different particles. Like, I don't know, you have many particles and they are all delocalized. You can then choose the coordinate fields to call all the points where the particle is delocalized as one point in your new reference frame. So there's no problem that you localize them. However, I don't know whether this will help you to solve the problem like the one which we had with the Earth and the particle, because you also want your dynamical laws to be symmetry under your change. And now, if you have a arbitrary delocalization of many particles and they maybe interact gravitationally, you might introduce very strange localization, very strange coordinate fields that will localize them. But then you don't know really whether this will help you to solve the problem, in a sense. I mean, maybe not even going beyond gravitation. Imagine that you have a Newtonian gravity. So you have a symmetry under global translations, but now you don't do global translations, not even quantum controlled global translation. So your dynamic law will go screwed. I mean, I haven't thought about that very deep, but I think you can do that, but the life might become also still hard. I don't know whether Flaminia wants to add something.
No.
Okay. To be honest, I would have a lot of questions myself, but given that It's already 5:30, and many people had the chances to ask questions. I would say we end the discussion here. Thanks a lot again to both of you for delivering these beautiful talks, and also for all the people here in the audience. I always love qmeets. We always have people asking nice questions. I'm happy to see you again in November, and I wish you a beautiful evening. Goodbye.
Thank you very much for having us.
Thank you. Thank you very much.
Bye-bye.
Thank you.
Bye. Thank you.
Bye. Thank you.
Bye.
Thank you very much.